Hi, I want to talk about sound intensity and how in human hearing that correlates to pressure amplitudes and displacement amplitudes of sound waves. Now when we talk intensity, there are two pieces that we usually could be talking about, and if we ever say intensity or sound intensity, we're talking about the physical definition of intensity, the power being delivered by a wave over the surface area with which that power is being delivered. That's what we mean by intensity. So for a sound wave, the intensity is going to be 1/2 times the density of our material times the speed of sound in our material times our traveling velocity squared, our angular frequency omega squared times our maximum displacement S max squared. In terms of pressure amplitude, our intensity is our maximum pressure displacement squared divided by 2 times the mass density and the speed of sound. And in acoustics, density times the speed of a wave shows up again and again and again and again. In acoustics, we're used to calling the speed of a wave c. In physics, we hold back on that. We call c the speed of one type of wave, the speed of light. So I'm probably going to refer to this as rho c at least once, but just for reference, for air at standard temperature and pressure, if you take the density multiplied by the speed of sound, you get a value of 415 newton seconds per meter cubed. Now, with sound intensity, the units we're dealing with are watts per meter squared. Power delivered over area. The other thing that people refer to, particularly when they're talking about loudness, is the sound intensity level, or it's sometimes just referred to as sound level. And that's what we measure using the decibel scale. And from the decibel scale, our sound level is 10 decibels times the log base 10 of the physical sound intensity divided by the standard reference intensity. So for sound and air, the standard reference intensity is 10 to the minus 12 watts of power per meter squared of area. So if we take a look at the human ear, depending on what frequency we're trying to listen to, depends on sort of what the minimum sound level it would take for us to be able to hear it. And there's always a maximum sound level too, at which there would be damage being caused to the ear. So the minimum sound intensity level at 100 hertz, towards the lower end of our speech and hearing processing frequencies, we need to have sound at an intensity level of 20 dB. The threshold of pain across all frequencies is 120 dB. So if we want to take an intensity level or a sound level and convert it into intensity, well, to undo this equation, I take my sound level, divide by 10 decibels, and that would give me the log of my intensity over my reference intensity. So I raise both sides as a power of 10, and my intensity would be my reference intensity times 10 to my sound level divided by 10 decibels. So if I wanted to take a look at the minimum for the case of 100 hertz sound, my minimum sound level is 20 dB. So I take 20 divided by 10, so that gives me 2. 10 squared is 100, and 10 squared times 10 to the negative 12 watts per meter squared is 10 to the minus 10 watts per meter squared. Now for the threshold of pain, 120 decibels divided by 10 dB gives me 12, and 10 to the 12 times 10 to the negative 12 gives me 1 watt per meter squared. So 1 watt per meter squared at any frequency hurts instantly. You will cause instant damage to your ear. So if I want to correlate these to pressure changes, well, my maximum pressure squared divided by 2 times the density and the speed of our sound equals our intensity, I. So the maximum pressure would be the square root of 2 times density times sound speed times that intensity. So if I have 10 to the negative 10 watts per meter squared times 415 newtons second per meter cubed times 2, I take the square root of that and I get a value of 0.000288 pascals, which is 0.29 millipascals. That's a very, very, very small change. When you think about right now, the pressure in bulk on your ear is about 100,000 pascals. So we can detect changes of tenths of a millipascal in 100,000 pascal in terms of being able to pick up on quiet sounds. That's a pretty huge difference to kind of try and think about. Now our maximum intensity is going to be 10 to the 10 times more. So the square root of 10 to the 10 is 10 to the 5. So the pressure where it starts to hurt is an oscillation of 28.8 pascals on a background pressure of 100,000 pascals. Now, to correlate that to a displacement, I could solve for my maximum displacement given my maximum pressure, and my maximum displacement would be my maximum pressure divided by the density, divided by the speed of sound, and divided by our angular frequency omega, which is 2 pi times our frequency f. So if I take 0.288 millipascals, divide by 415 newton seconds per meter cubed, divide by 200 pi radians per second, I end up with a maximum displacement amplitude at the quietest sound, weird structure there, of 1.1 times 10 to the negative 9 meters. 1.1 nanometers of displacement is enough for us to hear 100 hertz sound if our ears are deemed healthy. Now, at a displacement at 100 hertz of 0.11 millimeters, 110 microns, it instantly hurts. We can be damaging the detectors along our basilar membrane at that displacement in our eardrums. So our ears are some of the most special, careful, powerful detectors that we can detect in terms of their range of operation, in terms of frequency, in terms of their range of operation, in terms of sensitivity. If you work in an industry where hearing protection is recommended, follow those recommendations. Protect your ears, because once you lose sensitivity, that sensitivity is permanently lost. Thanks for watching.